In this next chapter, we're going to discuss atoms, molecules, and ions. And we'll begin with defining what the atomic theory of matter is. This is the theory that atoms are the fundamental building blocks of matter. And in the 19th century, John Dalton contributed quite a bit to this theory. So we see this table here of some of the tenets of Dalton's atomic theory, where in the first mentioned here, an atom is an extremely small particle of matter. So each element is composed of atoms. And we see this red ball here representing an oxygen atom, and then we see this blue ball here representing a nitrogen atom. So all atoms of a given element in number 2 here are identical. So every oxygen atom looks the same, and every nitrogen atom looks the same, but they look different from one another, as is the case with all the elements. In number 3 here, we see that atoms of one element cannot be changed into atoms of a different element, not through chemical means anyway. We can see that if we study nuclear chemistry, there's some discrepancy there where we can convert through decay, radioactive decay of nuclei, but for our purposes, this is true. We cannot make oxygen into nitrogen. And then when we form compounds, so now in number 4 here, we're combining different elements. The same relative number of the same kind of atoms will come together. So, for example, whenever we combine nitrogen and oxygen to get the compound NO, it will always be this 1-to-1 ratio. So we'll see down here, there's a law of conservation of mass that we should consider, that whenever there is a chemical reaction, the mass of the substance or substances present at the beginning will be the same at the end of the process. So this is called the conservation of mass, where we have the same mass of when we talk about reactions, we'll say the mass of the reactants will equal the mass of our products. And whether it's a chemical reaction or another type of process, we're always going to see this conservation of mass. So that leads us into the discovery of the atomic structure. So depending on what subatomic particle we're talking about, a different scientist contributed to that. So first we see here the electron, which J.J. Thomson is credited with the illumination of the electron here, the description of it. And we can see that his experiment involved streams of negatively charged particles, which emanated from cathode tubes causing fluorescence. And then he was able to measure this charge to mass ratio referenced here and obtain this value. So again, J.J. Thomson is credited with the electron discovery. Then we can see here this Millikan oil drop experiment. If you want to check out this video, it's explained a little more in detail, this process seen on the left here. But Robert Millikan determined the charge of an electron. So per electron, the charge is thought to be 1.6 times 10 to the 19th coulomb. So we won't really talk about this unit too much this semester, but this is the charge of a single electron. Then we have some more scientists down here. So radioactivity, which is in general the spontaneous emission of radiation from an atom. So just we'll say spontaneous emission of radiation from an atom. And Becquerel is quite credited with that discovery. Then we have Marie and Pierre Curie. They have also studied radioactivity. And then last, we have Ernest Rutherford listed here, which actually defined 3 different types of radiation. So we can see alpha particles, which are abbreviated like this with this little alpha symbol there. Then we have beta particles. And last, we have what's called a gamma ray or gamma particle. So these were defined by Rutherford. And then Thomson, the same Thomson reference before, had this plum pudding model for an atom where he thought that there was a positively charged sphere with small negatively charged electrons embedded in it, scattered throughout. Mainly because there was the assumption that the electron has very small mass, so it probably didn't take up, so very small, sorry, mass, so it probably didn't take up much space. But this was wrong. This was discovered to be wrong later on, this plum pudding model. So this was around 1900, and then Rutherford used those alpha particles that he described earlier. And if you watch this video here, the Rutherford gold foil experiment is elaborated upon. But he discovered this scattering of particles when he shot these alpha particles into the gold foil, and he helped to discover the atomic nucleus. So the nucleus contains protons and neutrons, which are more massive than the alpha particles, but also have a positive charge. So that's how we discovered that most of the volume down here of an atom is empty space. And these electrons kind of circle around our much larger nucleus in the center. So we have a small dense nucleus in the center, and then even smaller, less massive electrons circling far from that nucleus. So we'll continue in the next video with the modern view of the atomic structure.